Alright, specific heat capacity of a substance is the heat required to produce a 1 degree rise produce a 1 degree centigrade rise in 1 kg. Let me know when you've written this down. Noted?
Yeah. Yeah.
Okay. So how do we interpret this particular definition that we have just written? So if I've got two different substances, let's say I've got 1 kg gold and I've got 1 kg of iron, or let's say water. Okay. If I want to raise the temperature of, let's say they're both at the same temperature, 23 degrees centigrade, 23 degrees centigrade, and I want to raise temperature of each one of them up to 24 degrees centigrade. Are you following me?
Yeah.
So the amount of heat that I have to give to each one of them, would it be the same or would it be different?
Can you repeat?
I have got two different samples. One is that of gold, the other one is that of water. They are both 1 kg of mass,
Yeah.
right? And now they're both at temperature 23 degrees centigrade. And I
Yeah.
want to raise temperature of each of these samples to 24 degrees centigrade. So
Yeah.
in order to raise their temperature, I have to give them some heat.
Is there 1 kg of gold?
Hmm. Can't there be 1 kg of gold?
No, there can.
They
I
can be.
just didn't.
Hmm. Okay. So we have got 1 kg of gold and 1 kg of water. They are currently at 23 degrees centigrade. I want to raise the temperature of for both of them to 24 degrees centigrade. The amount of heat that I have to give to each one
Will
of
be
these
different
it will be different.
because every substance has a different heat
So
capacity.
excellent, excellent. So the amount of heat that I have to give to each one of them so that their temperature it raises by 1 degree centigrade, that amount of heat will be called specific heat capacity. All right. In order to
Yes.
elaborate this further, we have got this heat equation which is called Q is equal to M times delta theta times C, where Q is the heat energy, M is the mass of the substance, delta theta is the change of temperature, change in temperature, and C is the specific heat capacity.
This first is data.
First is heat.
What
Q
is this
Q
sign for?
Q is equal to M times delta theta times C. This is theta over here. So Q heat. I've written I've written all of them. I've written for all of them below what each of them is. Spec- okay. In your book, in chapter 5, I think they also use the symbol Q. Hmm. Just a second. Mm, mm, anyhow, moving on. So this is the formula, and if we want to understand this particular formula, there is one more thing. So why is it disconnected over here? Should I reconnect it? Maybe I should reconnect over here too. Hmm. One second. Okay. The next thing that we have is the thermal capacity of a substance. What is the thermal capacity? Okay. For specific heat capacity, we said that we want to raise the temperature of 1 kg of mass of a substance, right? But what if the mass of the substance is other than 1 kg? Then what's the amount of heat that we have to give to that particular substance so that its temperature rises by 1 degree centigrade? So that is what we call thermal capacity. If you could write down the heading thermal capacity. Hmm. Can't you sit in a different room where there would be less disturbance? Hmm. Quantity of heat needed to raise the temperature of whole body by 1 degree centigrade. Thermal capacity and specific heat capacity. Specific heat capacity is for just 1 kg of the substance. Thermal capacity is for whatever mass. Hmm. Quantity of heat needed to raise temperature of whole body by 1 degree centigrade. Of whole body by 1 degree centigrade. And and thermal capacity is equal to mass times specific heat capacity. Okay. Let me give you a few questions. If you could solve these. Yes. Q is equal to m times delta theta times C. It isn't it isn't necessarily the formula for specific heat capacity. It's the formula for it's called heat equation. So it is Q is equal to m times delta theta times C, specific heat capacity. Okay, okay, okay. So now let's attempt these questions. Just a second. You can see the questions. All right, go on, attempt these. The SI unit for thermal capacity C. The SI unit for thermal capacity will be joules per degree centigrade. Why? Because joules per degree centigrade. Here is the reason why. Let's see. First, we have to find out for specific heat capacity. So we have got Q is equal to mc delta theta. So this is in joules, mass is in kg, or if I just rearrange this so as to make C the subject, it will become C is equal to Q divided by m times delta theta, right? So Q is in joules, mass is in kg, and delta theta would be in degree centigrade. So this is the SI unit for specific heat capacity for C. And when we are doing thermal capacity, for thermal capacity we say mass times specific heat capacity, right? So mass is in kg, and specific heat capacity we just found out joules per kg per degree centigrade. So kg would cancel kg, and we'll be left with just joules per degree centigrade. So this is the SI unit for thermal capacity, joules per degree centigrade, and for specific heat capacity, it's joules per kg per degree centigrade. Alright, so what's your answer? What is the thermal capacity of the substance you got? 1500. But what about how much heat is needed to raise the temperature? This first question. Here it's written m times c times delta theta. What's the change of temperature? Hmm. It will be 15,000. So 15,000 watt. The unit for Q will be 15,000 joules. Excellent. Next question. Hmm. You have to do 5 into 10 into 300. So 5 into 3000 will be 15,000. Next, question 2. Question 2 quickly. You tell me. Hmm. It will be 2000. 2000, correct. E will be 200. And what will be the unit? Hmm. We read it joules per kilogram per degree centigrade. It's read this way. For C, it will be 1000. Mm, The last one question, Stuart, would be the answer. Are you there? Question number 3, what's the answer? Let's say a substance. The specific heat capacity of gem would be higher. If the specific heat capacity of gem is higher, it would take longer to cool down as well. So substances with a higher specific heat capacity, they take longer to heat up. Specific heat capacity because it is taking longer to cool down. Okay. Then we have got one small thing that we need to add to this, and then we are done with the topic. We can move to the past paper practice. Um, that specific thing that we are left with is specific latent heat. Do you know what's specific latent heat? Latent heat. Mhm. Let's first write down the heading: specific latent heat. Okay. If I've got a piece of, let's say ice cube. Okay, and I start give ice cube. I start giving it heat. As I give it heat, its temperature would rise. Okay, its temperature would keep rising until a point when it stops rising, even though I'm giving it heat. And then after some time, it will melt. Did you follow what I just said? Okay, so there is a substance to which I'm giving heat, and initially when I give it heat, it would increase the temperature of the substance up till a certain point. After that point, it will stop raising the temperature of the substance, and then it will convert the state of matter of the substance. So this amount of heat which I was giving to the substance but which did not result in raising the temperature of the substance, actually this heat was being used for what? It was being used to change the state of matter of the substance. Are you following me? Keep your mic unmuted. Just sit in an area where there is less background noise. Is it like hmm hmm okay. So if I've got a substance and I'm giving it heat, initially when I give it heat, it raises the temperature of the substance. Then I give it more heat. I mean, I'm giving it the same amount of heat, and now the temperature, it does not rise anymore. Then where is this heat going? What function is this heat performing? It is performing the function of changing the state of matter. So it is converting this solid to liquid. That is what this heat is doing right now when it is not raising the temperature of this substance. It is breaking the bonds between the molecules of the matter so that they move further away, as in the case of a liquid. The bonds between the molecules of a solid are stronger, and the molecules, they are situated close together. But when we give it heat, initially the heat was being used to raise the temperature, and then the heat, it was being used to convert the state of matter from solid to liquid. And then if I give it more heat, once its state has been changed, it would again increase the temperature of the substance. So once it has converted into liquid, it would now, the same amount of heat that I'm providing it, it would now again start raising the temperature of the substance. So in order to write the definition of what this specific latent heat is, and this specific latent heat, we study two types of specific latent heat. The first one that we study is specific latent heat of fusion. So specific latent heat of fusion of a substance is the quantity of heat needed to change unit mass from solid to liquid needed to change unit mass from solid to liquid without temperature change. Why do we mention without temperature change in this one? First write down the whole definition and then tell me why do we mention without temperature change in this definition. What if I am told that this was the ice cube initially at 0 degree centigrade, and now I gave it some heat, and that heat converted it into water at 7 degrees centigrade? Can I call this heat specific latent heat of fusion? Why not? Exactly. So I'm just concerned with the amount of heat that only changes the state of matter. If there is some heat which is also changing, which is also raising the temperature of the substance, that's not the heat that I'm talking about. The specific latent heat of fusion is only the heat which is changing the state of matter of the substance. And how do we calculate it? We use the formula. We say Q is equal to mass times latent heat of fusion. All right. Latent heat of fusion. Usually with this L we write a small f to show that this is latent heat of fusion. The same way we have got latent heat of fusion, we have got another thing which we call specific latent heat of vaporization. So we'll write specific latent heat of vaporization LV of a substance is the amount of heat needed to change unit mass from liquid to vapor without change of temperature. So for fusion, it was changing the state of matter from solid to liquid, and for vaporization, it is from liquid to vapor. Or for latent heat of fusion, it was changing the state of matter from solid to liquid. For latent heat of vaporization, it is changing the state from liquid to vapor. Both are for unit masses. Okay. Okay, then there is this one small thing that we need to know. What are the differences between evaporation and boiling? What is evaporation and what is boiling? Are they like two different names for the same thing, or are they two different things? Is there a difference between boiling and evaporation, or are they two the same thing? What's the difference? Okay. First of all, what is boiling and what is evaporation? The first thing. So change of state from liquid to gas, and evaporation. What is evaporation? Escaping of molecules of a liquid from its surface. Right? The second thing you mentioned, boiling happens at a specific temperature. whereas evaporation happens at all temperatures. Okay, any other difference? Takes place only at surface of liquid. Done? Okay, good. Next, I want you to give me what are the factors that would cause the rate of evaporation to increase or decrease. Factors affecting rate of evaporation. Hmm. Hmm. Last one was, and the one after it. So there are four factors: temperature, surface area, wind, and dry atmosphere. If there is higher temperature, there would be more evaporation. If the surface area is spread over, why is this rate of evaporation higher for larger surface area? Did you get the question? Hmm. I said, why is rate of evaporation higher when the surface area of the liquid is more? Can you hear me now? Hmm. Hmm. I was saying, why is rate of evaporation higher when the surface area is greater? Mhm, 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 mhm. There is more evaporation happens at the surface area, right? And obviously, if there is more surface area, there will be more evaporation. Okay, let me put a few questions up here. You can solve these, and then perhaps we will call it a day. There are quite a few. So start with these, and I'll put more over here. Hmm. Be careful about units, be careful about all the information. Some questions, what are we finding? Hmm. The amount of heat. You tell me, I gave you all the formulas. You will have, sir. You'll have to give it an attempt and then you'll have to tell me the answer and explain me why you solved the question the way you solved it. All of these. Hmm. So complete all the parts of one question and give me that, then all the parts of next question, then we'll discuss that and so on. Yes, sir. Question one solved. Five. Hmm. That is the formula that we have, but answer is wrong because you perhaps used the wrong values. Look over here. This is specific latent heat. It is not joules per kilogram. It is joules per gram over here. Alright. So one thing, we do not need to change the mass from uh, grams to kilograms. One thing. The other thing is, right now we are changing ice to water. So which one will we use? The one for water or the one for ice? This is specific latent heat of fusion, and this is specific latent heat of vaporization. Since right now we are talking about conversion between solid and liquid, we will use the latent heat of fusion. So Q is equal to mass times latent heat of fusion, which will be 10 times 340. If there is any confusion, go ahead and ask me. Yes, sir. Any confusion? You took what? That is specific heat capacity. That is C. Why are we taking this 340? Latent heat. And why are we using latent heat over here? What's the formula? Why are we using latent heat? Why are we not using the formula mc delta theta over here? No, wrong. Wrong. We are using this formula because this is the formula that we use when there is change of state of matter. Specific latent heat is the heat that is used or given up when there is change of state of matter from solid to liquid, from liquid to gas. And specific heat capacity is the heat which is used when there is no change of state of matter. In the same state of matter, we are just increasing or decreasing the temperature of something. Then we use the formula for specific heat. Right now, are we changing the temperature or are we changing the state of matter? In question 1a, I asked that in this particular question, are we raising or changing this temperature of the substance or are we changing the state of matter of the substance? State from solid to liquid. So if we are not changing the temperature, we won't use the formula of specific heat capacity or the formula in which we use the specific. That is the one that we use when we are increasing or decreasing the temperature of a substance in the same state. If the state of matter is changing, if it is changing from solid to liquid to gas or gas to liquid or liquid to solid, then we will use the specific latent heat. Understood now? It's not because one is shorter and the other is longer. Each formula has its own use and it will be used in certain conditions and only there it will be used. Can't be used everywhere. Anyhow, next part 1b. Just finish this 1b and the rest is your homework. Hmm. In fact, take a screenshot. Take a screenshot. We'll keep it till here. Inshallah, onwards we'll discuss in the next class. All right.